Hi kids, welcome back to our series of video lectures. This is the first lecture for our electricity unit, and the topic is atoms, subatomic particles, conductors, and insulators. The essential question for this slideshow is, what are subatomic particles and how do they behave? This might be a little bit of a review depending on what you've covered in middle school science, so you can go through this quickly if you already know some of this information, but if you don't, I would really take your time because this slideshow has a lot of the fundamental things that you're going to need to be able to understand to have success in this unit. So let's start with atoms. Atoms are the building block of matter. If you zoom in on anything that you're looking at, you're going to discover the closer you get, the more chunky it looks. So if I zoom in on that ant, I'll start to see little parts of that ant. But if I zoom in on those parts, eventually you get down to seeing these little Lego-looking pieces that are the atoms that are making up everything. There's 115 different types of atoms, and they are known as the elements. For a long time, scientists thought that the atom was the smallest building block you could get, but eventually new technologies allowed us to look inside atoms, and we found even smaller particles known as subatomic particles. Each atom is made up of these subatomic particles. They're called the protons, the neutrons, and the electrons. This is kind of a classical view of the atom. It's actually more complicated than this, which you'll learn about in chemistry, but the basics hold true. We have a really tiny, dense area right in the middle of the atom known as the nucleus, and this is where the protons and the neutrons are all packed together in a really tight space. The electrons get to whiz around the outside in paths called orbitals, and overall, make up most of the volume of the atom, even though they're really small compared to the nucleus. In this class, the two subatomic particles that we'll be paying the most attention to are the protons and the electrons. So this slide is going to kind of compare and contrast the differences between those subatomic particles. For starters, protons have a lot of mass. They're much, much heavier than electrons, which have teeny tiny masses. So most of the mass of us is made up of protons. I would say almost all of it is protons and neutrons, and only a tiny bit of your mass is made up of electrons. A second really important thing is that protons, as we mentioned in the slide before, are stuck in the nucleus of the atoms. They're in that tight area and they're not allowed to leave. I have an asterisk there because if a proton does leave the nucleus, what happens is known as nuclear fission, aka a nuclear explosion. So obviously we're not going to be doing a lot of that in this class. Electrons, on the other hand, get to orbit freely around the nucleus. They can even move easily from atom to atom. So when we talk about the movement of subatomic particles in this class, it's going to be basically entirely electrons because we're going to try to avoid having nuclear explosions, which is what would happen if we allow our protons to move. Protons and electrons have a property known as charge, which is going to determine how they interact with each other. Charge is kind of like mass for other objects. It's a conserved property, and it is the reason why we have electric forces and electricity. All has to do with this charge. And protons, charge is a new variable for us. It's going to be the variable Q, and we'll talk about the units in a minute. The protons have a positive charge. So for the purposes of this class, we're going to assume that Q for a proton is +1 coulomb. Coulomb is the unit of charge and can be abbreviated with a capital C. There's a little asterisk because it actually isn't exactly 1 coulomb, but that's going to make our math a lot easier in this class, so we're just going to go forward with it as 1. The electrons are the exact opposite of the protons. They have a negative charge, and in fact, they have exactly the same amount of negative charge as the proton has positive. So Q for an electron is -1 coulomb. When you bring a proton and an electron near each other, or two electrons or two protons, they experience a force from each other. And the direction of that force depends on whether the charges are positive or negative. So if you have a big positive proton coming near a negative electron, The opposite charges are going to be attracting each other. Those two particles are going to try to zoom towards each other. You may have heard opposites attract, and that's true in electricity. However, if I try to bring two similar or like charges together, if I bring two electrons close to each other or two protons, instead of attracting, they're going to be pushing away from each other, which we call repel. That means to push away from each other. Since the subatomic particles and the atoms are so small, every normal object that you would ever see in your world actually has millions and billions and zillions of those electrons and protons, and it would be really a challenge to try to keep track of all of those. But the good news is all we really care about is the sigma charge, or the unbalanced portion of those electrons and protons, because it's this unbalanced amount of charge which is going to ultimately determine whether two objects are attracting or repelling and how much they attract or repel. Now, it turns out that most objects and most systems have a sigma charge of 0. What this means is there's exactly the same number of electrons and protons and protons in the object. So every -1 electron is canceled out by a +1 proton, which gives us a sigma charge of 0. So every ball, every car, you, this table, they don't have any sigma charge usually because we have the same number of each of those subatomic particles. It turns out the entire universe also has a sigma charge of 0, which means there's exactly the same number of electrons and protons in the universe. This is actually one of the great mysteries of physics. If it wasn't that way, life as we know it wouldn't exist, but there's no real reason mathematically why there should have to be exactly the same number. So let's count ourselves lucky that we were born into this particular universe. Another word you may hear us say when the sigma charge of an object is 0 is a neutral charge. That just means that we have the same amount of each. It's easy to find the sigma charge in an object. All you have to do is add up all of the individual charges. So if I look at this object here that has 4 protons and 4 electrons, sigma charge is going to be 0 coulombs because they're all canceled out by their opposite charges. This object here has 4 protons and 6 electrons. Since electrons are negative, we have a sigma q of -2 coulombs. There's 2 extra electrons. This one has 4 protons and 1 electron, so sigma q is going to be +3 coulombs. You'll notice that, as I mentioned earlier, the protons are not moving and the electrons are the things that kind of move around this object because they're mobile, they're able to move. So a couple facts about the electric force, which is that the strength of the force that attracts or repels objects that are charged. As I mentioned before, any two particles or objects that have an unbalanced charge, a sigma charge, are going to experience an electric force. Along with gravitation, the electric force is known as one of the fundamental forces of nature. There's actually only 4 of them, so this one's a big deal. The strength of this electric force has a direct relationship with how unbalanced the charges are. So the more unbalanced the charges are on an object, the stronger that force is going to be. And there's also an inverse relationship with the distance between the two objects. So the closer that the objects are, the stronger they're going to be attracting or repelling. There's a little asterisk there because it's actually a special kind of inverse. It's called inverse squared. I don't want to make that a big deal in this class, but it basically means that the distance is a big deal. Because the electric force gets stronger the closer two objects are, it actually means that nothing in this universe is ever actually physically touching anything else. And this is kind of a cool idea. You feel like you're touching your chair and your computer right now, but you're not, because the electrons in your finger, which are whizzing around the outside of those atoms, the closer they get to the electrons on your keyboard, for example, the stronger they repel. So you can push all you want, but you're not actually ever touching anything because that force gets really, really, really strong the closer you try to get those objects to each other. This electric force is a really big deal, as I mentioned earlier. All of the other forces that we've learned about, except for gravity, actually are the electric force. So the normal force, as we mentioned, when two objects try to touch each other, it's really actually an electric force. Tension is an electric force that's holding together that rope. The electrons in the rope are holding to each other. The spring force has to do with the molecules, the shape of the molecules in the spring. Friction is an electric force. It has to do with the little bumps and ridges repelling from bumps and ridges of objects nearby. So even though we've given them other names, if you could really zoom down to the root causes of those forces, everything is actually electric. So the world around us is full of electrons and protons, making up all the materials that we interact with every day. But certain materials respond to electricity different than others. And you can loosely categorize everything around you into two categories: conductors and insulators. For any material, the protons are going to stay in the nucleus of each atom, because if the protons move, we get an explosion. And also for any materials, it is possible for the electrons to move from one atom to another. The term conductivity refers to how easy or difficult it is for these electrons to move. One category of materials is known as the insulator, and these are materials that have a low amount of conductivity. In other words, the electrons do not move very easily from one atom to the other in an insulator. Another way to think about an insulator is this is something you could safely stick in a light socket. As we all know, there's really high energy electrons inside those light sockets, but if you stick an insulator in there, those electrons can't move out to electrocute us. So if you can picture something you could stuff into a light socket, it would probably be an insulator. So the reason that electrons don't move very easily inside of insulators is because the nuclei, which is plural for nucleus, of an insulator holds on really tightly to their electrons. So the electrons are moving around inside the atoms, but they can't really escape on their own easily. If you could zoom in on an insulator, you'd see that electrons and protons kind of come in little matched pairs. So those electrons are moving around, but they're staying really close to their little home. Sometimes I picture this as Velcro, little subatomic particle Velcro. The electrons can move, but they can't move very far. Some examples of insulating materials include wood, rubber, plastic. Those are all really good insulators. Air is a good insulator. So the other category of materials is known as a conductor, which is a material that has a high amount of conductivity. In other words, the electrons can move easily around those atoms from one atom to the next. These are materials that you're not going to want to stick in a light socket because the high energy electrons in the light socket could easily come out and cause electrocution. The atoms are happy to share their electrons. The electrons can move anywhere in the material, and they can also easily move on and off of the material onto other conductors as well. So if you touch two conductors to each other, they just happily share electrons all over the place very quickly. So if you could zoom in on a conductor, it would look a little bit different. We still are neutral. We have the same number of protons and electrons, but those electrons can go wherever they want. So they might be piled up in one corner, or they might be all spread out, but you can't really count on them being close to their protons. Some examples of conductors: metal and water, as we know, things that electrons can move through easily. We're almost done with the slideshow, but I wanted to talk about a process called polarization because it actually is really a big deal in the real world and is probably something you've noticed a lot. So polarization is what happens when you have one object that has a charge and you're getting it close to other objects, any other object. So for example, you pull your sock out of the dryer and it sticks to you, right? That sock had a charge, you were neutral, but it still wanted to stick to you. And the reason it did that is because of polarization. So what happens when you have that object with a really big charge and you put it near a neutral object? So on the left, I have an object with a really large negative charge, sigma charge. There's a whole bunch of unbalanced electrons and only 4 protons. So we have a really big negative sigma q. On the right, I'm going to have a neutral object. I'm going to make this a neutral conductor just to kind of emphasize what's going on. Right now, I only have the 4 protons on there, but if I add my 4 electrons to make it neutral, you'll notice that those electrons are not randomly distributed in that object. They actually moved as far to the right as they possibly could. And the reason they did that is because like charges repel. Since the whole other object is negative, the negative charges inside that conductor on the right were repelled, and they moved away as far as possible. The protons, you'll notice, they can't move because they're stuck in their nucleus. So this object on the right is still neutral. It still has balanced charges, 4 and 4, but it's almost like it's got 2 halves or 2 poles, which is why this is called polarization. We've got a positive half on the left, because all the electrons are gone, and a negative half on the right. So we're neutral, but we have 2 poles. And the result of this is actually 2 different forces, 2 different electric forces. We have an electric force pushing to the right from the electrons that are being repelled, and we have an electric force pulling to the left from the protons on the left half. So the object itself actually has 2 forces acting on it, repulsive and attractive at the same time, because it's got both of those kind of subatomic particles in it. So even though we're a neutral object, we can still experience electric forces, because if you zoom inside that object, we have little tiny charged objects. Now, as we noticed with our sock out of the dryer, it actually attracted to your body, and polarization always results in attraction, because even though we have the same number of electrons and protons on each half, the positive half, you'll notice, is a lot closer to that negative object than the negative half. So since that half is closer and the electric force depends on distance, that pulling attractive force ends up being a stronger force than the repulsive force on the other side. So overall, the net, or the sigma force, the unbalanced force, ends up being attractive when you have an object that is being polarized. So that's it for the content of this show. I know this was a pretty dense one, so hopefully you guys took good notes. But I do want you to think back and revisit our essential questions. So what are the subatomic particles, and how do they behave in the materials that we see around us? A couple things to kind of focus on: the types of the subatomic particles, some similarities and differences between them, and how do they act when they're close to each other. And the last thing is what determines if a material is a conductor or an insulator. Sorry, I missed that R there. All right, thanks for watching.